Hey AP Calc, welcome to 6.2 Trapezoidal Sums. This is just another way to approximate the integral, which again is the area under the curve down to the x-axis. And instead of Riemann sums, which are rectangles, we're going to use the trapezoidal sum, which uses, you guessed it, trapezoids. Alright, for those of you that it's been a long time since geometry, this is a trapezoid right here in all its glory. A trapezoid is a quadrilateral. It's got 4 sides. 2 of those sides have to be parallel to each other, and the other 2 don't. If they were, it would be a rectangle. Okay, the height is the distance between those parallel sides, and those parallel sides are called the bases. Now, this trapezoid could look like this, too. It doesn't really matter how it's positioned. We still have a set of parallel sides and a height. But this height is now not vertical like we think of height being. The height is just the distance between the 2 sides that are parallel, basically. So in calc, when we are finding trapezoids, they're going to look like this. They're going to be on their side. And the height, since it's a horizontal measurement, is the distance between the first x value and the second. And then these actual heights, the vertical sides here that are parallel to each other, are the y values that we'll get on our function. Okay, what is the area formula for a trapezoid? It's half the height times the sum of the bases. And remember, height, distance between the 2 bases. Okay, let me just do a quick sketch so I can explain what I've been talking about. So we have our xy axis, and I'm going to draw a function in blue. And we'll call that f of x. Okay, so we have this function, and we want to approximate the area under the curve. Let's go until 4. So from 0 to 4, 1, 2, 3, 4. Okay. All right, and we want to use trapezoids. So I will draw the first trapezoid in purple. So if we go up to the y value, so f of 0 right here, and then to f of 1 right here. This trapezoid will be slightly under the curve, and it will look just like that. So it basically looks like this guy. This guy could fit right here, you know? So the height is really the distance between our x values, which we call delta x. So the area of this trapezoid, I'll do it in purple since that's, so the area of that trapezoid is 1/2 delta x. Then what are these bases? Well, the bases of this guy are the actual heights, right? They're how tall it is on either side. That was weird. All right, so what is that? Well, in this case, it's f of our first x value and f of our second x value here. All right, so the area of this trapezoid, it's f of our left x value, which is 0. It's whatever height is provided when x is 0. And then whatever height's provided when x is 1. I didn't give you an actual function, so you could plug it in and get numbers, but who cares? It's f of 0. That's this length right here. F of 1 is this height right here, that length. Cool. So that's the area of that first trapezoid. If we look at the next trapezoid, I'll just pick a different one. Let's do the trapezoid from 2 to 3. Okay, what would the area of that one be? Well, it would be half the height of the trapezoid. But remember, the height of the trapezoid is the distance between the x values, so it's delta x, which in this case is just 1, times the sum of these two sides, which in this case is f of 2 and f of 3. So this is essentially what we're doing. I mean, we're using a trapezoid, and the height is delta x. So how can we figure out what delta x is? Well, in this case, our A and our B, we wanted to approximate the area under the curve from 0 to 4. And I wanted to use 4 trapezoids. So here's the last two. All right, those are the 4 trapezoids. The first one in purple, black, green, and then black. All right, how can we find delta x? Well, we'd find delta x, the distance between each of the x values, by taking our upper limit of 4 minus our lower limit of 0. And divide it by how many trapezoids you're told to use. In this case, it was 4. So our delta x was 4 divided by 4, which was 1. In general, delta x is your upper limit b minus your lower limit a divided by how many trapezoids you're asked to use. We saw this formula a little bit with the Riemann sums, but I just want to point it out in case logically it doesn't make sense how many trapezoids to use or like how long each distance should be. You can use this formula. Okay, here's our first example. We want to approximate the area beneath f of x equals x squared plus 1. So just a simple parabola with a y-intercept of 1. And I've screen grabbed it from 0 to 3. So I have it going by 0.5s just because that's how the calculator that I used did it on this app. But let's take a look at how we can draw those 3 trapezoids. Again, I'm very visual, so I'm just going to draw them using purple. Now, before we get to drawing them, I want to figure out what delta x should be. Remember, delta x, the distance between our x values, like the bottom part of our trapezoid, is b minus a divided by n, where b is our upper limit, a is our lower limit, and n is how many trapezoids we want. So what we want to approximate, the area beneath that, we're approximating this, the integral from 0 to 3 of our function. So this is the upper limit, 3. This is the lower limit, 0. N is 3. So this one's pretty easy just because we want the distance from 0 to 3. And we want 3 trapezoids, so each one has to be 1 unit long. You can just kind of think about that. But this would be 3 minus 0 over 3, so our delta x would just be 1 here. Okay, so that means that my first trapezoid will connect a length of 1 here, delta x, and these will be the heights. And then I'm going to connect them, not making a rectangle anymore, I'm making a trapezoid. So as you can see, this trapezoid is definitely an overestimate of that area, but not by as much as like the right Riemann sum would have been. And that's because this function here is concave up. It's arcing upward. It would hold water. And so when we're concave up, our trapezoids are just going to go a little bit above the function since it's curved like a U. And so that straight line over it would be above it. So this is going to end up being an overestimate, but not too severe. Not too severe. Okay, so let's take a look at our first trapezoid and let's figure out the area of that trapezoid. So I'll call this our first t. Okay, so our first t, so it's 1/2 delta x. Remember, the area of a trapezoid is 1/2 delta x times your first f value times your second f value, right? So this area here would be 1/2 of delta x. Delta x is 1. And then we have to have our two heights, right? So in this case, our first x value is at 0. That height provided is 1. How do we get that? We could plug 0 into this function and we get 1 out. Our second height, right, our y value provided by the next x coordinate, if we plugged 1 in, we get a height of 2. So f of 1 is 2. We could just see that on our graph, or we could like make an xy chart or use our function. So we have the first height is 1 and the second one is 2. All right, I'm going to make that a little smaller so we can just write what the answer is to that. All right, so we end up getting 1/2 of 1, so 1/2 times 3, which is 3/2. Cool. All right, let's do our next one. Do it in orange. So we have this coordinate again. We move 1 unit over, and then 2 goes up to 5 here. Okay, this trapezoid is definitely, it's a slight overestimate because it's a little bit above the green curve. This is another trapezoid. So it's 1/2 of our delta x, which is 1 unit. And then this is 2, and this height is 5. All right, so that will give us 7/2. And then our final one, I'll do in blue. That trapezoid is 1/2 delta x, again, which is 1. And then the heights of our trapezoid, or the bases, however you want to look at it, are 5 and 10. Again, we get that from if I plug 2 into the function, I'll get 5. And if you plug 3 into the function, you'll get 10. So 5 plus 10, which is 15/2. Okay, finding our total, I'm going to add, they're all halves. So I'll add 3 and 7 to get 10, plus 15 is 25. So our trapezoidal sum with 3 trapezoids is 25 over 2, which is 12.5. Cool. Okay, this next example is some trig, just because you will definitely see it. I provided part of the unit circle from 0 to pi, just so we can know values in case we don't know them. But let's graph y equals sine of x from 0 to pi using the trapezoidal rule with 4 trapezoids. So let's figure out what our delta x would be. Our delta x is b minus a, so our upper limit minus our lower limit, pi minus 0, divided by n, how many trapezoids? So our delta x is pi over 4. So we're going from 0 to pi, and we obviously want to split it into 4 parts, so each one is 1/4 of a pi. That makes intuitive sense, but we can just use this formula if we need to. Okay, so I'm going to split it in half, pi over 2, and then in half again, and then this would be 3/4 of a pi. Okay. Now, if we look at sine, sine's the y value, right? So at certain spots, it's pretty easy to graph. So at 0, which is here, sine is 0. Pi over 4, the sine is root 2 over 2, which is like 0.707, I think. Then at pi over 2, the sine is 1. At 3 pi over 4, it's back to root 2 over 2. And at pi, the sine goes back to 0. So I'm going to graph those easy ones. So it's 0, and it's 0 here. And then it goes up to 1. That's the greatest sine can ever be at pi over 2. The sine function just looks like a curve, right? It keeps going, like it would keep going like that, if you remember that from last year. But we don't need to keep going there. So this is just what we want. Then I'm just going to mark that this is like about root 2 over 2. Okay. And root 2 over 2, I believe, is 0.7. Let me just double check. Yep, 0.707. Okay. All right, let's make our trapezoids. So I'll make those in blue. So we want 4 of them. So our first trapezoid will be here. And it is a triangle. Our second trapezoid will be here. Our third trapezoid will be here. And our last one is also a triangle. And this sine curve is concave down. It's opening down. Therefore, our trapezoidal sum will be an underestimate because of the arc downward. Now, this first one I just didn't draw super well, and so it looks like it's exactly on the curve, but technically these 3 are the best looking trapezoids there. So it's an underestimate. So let's find the area of each trapezoid. Let's do our first one. We'll have 1/2 times delta x, which is pi over 4. And then times our heights. Our heights are 0 and root 2 over 2. Okay, I did a little rearranging there with pausing it because we're going to need a little more room. Okay, our next one is 1/2. Again, our delta x, which is pi over 4. That's the distance between here and here. And then what are our heights? Well, this one's root 2 over 2. It's the height we've already used. And then this one's 1. Okay. Plus, our next one is, again, 1/2 pi over 4. Plus our heights, which are 1 and root 2 over 2. And our last one our heights are root 2 over 2 and 0. All right, now we have 4 terms. This one, this one, this one, and this one, 4 trapezoids. So what I'm going to do is factor out this part of each one. And let's think about what 1/2 times pi over 4 is. It'd be pi over 8, really. So this each time is really pi over 8. So we can just bring that out front. And then they were being multiplied by a 0. No need to write it. a root 2 over 2, a second root 2 over 2, a third one, and a fourth one. So we ended up having 4 root 2 over 2s. Then we also had this 1 and this 1. So that makes plus 2. Don't even need all that room. Okay, how can we simplify this? Well, 4 over 2 is just 2. So we have pi over 8 times 2 root 2 plus 2. That's fine. If you wanted to put that in your calculator, I'll see what we end up getting. And it's approximately 1.896. Okay, our last example is from a table, which I hastily have put into a function form. Again, you know, this table here only gives us values at these 5 points. It doesn't tell us the connectivity of the function. So I'm saying that our function is concave down. I tried to draw it as concave down as I could. It kind of has an arc. It's pretty linear here, and then it turns to concave down, like opening downwards. And then we want to approximate the integral from 0 to 10 using a trapezoidal sum. Now, since we have 5 points, we're going to end up having 4 trapezoids. It's kind of similar to the Riemann sums in that way. So I just made it visual again for ease, but you don't necessarily need to make it visual. So our first one, our first trapezoid, looks like that. And we can't really use a formula for delta x here because delta x is different every time. If you note, the distance between these two x values is 2, but the distance between these is 3. So each trapezoid is going to have a different delta x. So our first trapezoid is half of that delta x, half of 2, times the heights of the trapezoid, those side lengths, so 2 and 3, which we get from here. So that one is 1 times 5. All right, let's try our next one. So the next one I'll do in purple. So that one is half, and now our delta x is 3 because the distance between 2 and 5 is 3. And then our heights of our trapezoid are 3 and 7, or sorry, 3 and 5, my bad, which we get from right here, or the graph. Okay, so we have 3 halves. Actually, I'm going to do it this way. This is 8 times a half, right, which is 4. And then times 3. So we'll get 12. So we can multiply in any order. Then the next one I'll do in green. Okay, that trapezoid, the delta x is 2 again because it's the distance between 5 and 7. And our heights, our y values, are actually also 5 and 7. So that also gives us 12 as a total. Go ahead and do the last one and then add them together. Okay, we end up with a trapezoidal sum of 51.5. Now we want to know, is this an over or under estimate? Now you can't go by my drawing that well just because I just sketched it very quickly on this app and it doesn't look wonderful. But since we know something's concave down, so if we were to draw something that's concave down, right, it in general looks like that. And if we were to make trapezoids under that, which this is just something in general, if we were to make trapezoids under that, note how the trapezoids are not going to quite reach the actual area. There's still a tiny little piece of excess that they're not quite covering. And so when we're concave down, the trapezoidal sum is going to provide us an underestimate of the actual area. Now, if we had something that was concave up, which in this case it's not, but if we had something that's concave up and we were drawing trapezoids, I'm going to do that a little bit better here. And we were drawing trapezoids underneath it, those trapezoids would provide an overestimate of the area that's actually underneath the black function that I drew. So if it helps to just sketch and see, you can, but since we're concave down here, our trapezoidal sum will be an underestimate of the actual area. Hello, okay, your assignment for this section is not going to fit on this screen, so it's a PDF. It's just like a worksheet basically that I converted to a PDF, and it has 5 problems on it. It's not going to be due until Tuesday, right? So you won't have a new assignment on Friday, just FYI. And I'll talk about that on Blackboard. I'll make an announcement. But anyway, this is going to be due Tuesday, not Monday, because we have a in-service day. So this is going to be Tuesday at noon. Let's see. That is Tuesday the 24th. Okay, I will put this into Blackboard under the assignment so you can get it there. I'll also shoot it out in an email when I release the video. I would recommend joining me on Zoom on Thursday or Friday if you are confused on anything, and then you have kind of like the weekend to make any corrections over this week's work using my feedback and to complete this assignment. Take care, guys.